Perfect. There we go.
Hi, we are the group doing reconfigurable manufacturing systems in the pharmaceutical industry. My name is Tobias Enoch, and I'm joined by Marcus Adams, Jack Aylesworth, and Talia Brooks. Looking at our agenda for today, we're going to start with a brief introduction, followed by a literature review of specific applications of RMS in the pharmaceutical industry, followed by a methodology and system analysis section looking at our specific case study, bookended by a conclusion. So, the first question you might have is what is RMS? Broadly speaking, a reconfigurable manufacturing system, or RMS, is any machine system with the ability to change functionality without drastically sacrificing reliability or cost. To achieve this, RMS systems are made of interchangeable modules, both software and hardware, that can be switched out with one another, adjusting the overall manufacturing process to match market demand, implement new technologies, or even change the product being manufactured entirely. The base goal of RMS is to manufacture a family of similar products to exactly match market demand as closely as possible. Looking at some of the design philosophy that went into RMS, RMS emerged in the early 90s, taking sort of components from FMS and DMS. So FMS, or flexible manufacturing systems, are able to achieve high flexibility, create a high range of products, but often struggle to achieve volume. Where dedicated manufacturing systems are good with high value volume production, but can't really achieve that same flexibility. So, for example, the first image we have here is Mullen's System 24. This was one of the first flexible manufacturing systems developed in the early 1960s, and it utilized some of the growing computing power at the time. It was a fully palletized machining center, meaning that there were different units that could perform different machining operations and pallets of raw material that would travel between each of these individual units for work to be done on them. This was extremely flexible and could really produce anything that could be programmed onto those machines, but it really struggled in fulfilling high volume orders. By contrast, something like this bottling plant pictured here would be a dedicated manufacturing system. And it's very, very, very effective at efficiently bottling this specific kind of bottle with a specific type of liquid. You get a lot of output, but it's very difficult to change this sort of system or reconfigure it to work with a different beverage, a different bottle, or achieve a different final result in general. The goal of RMS then is to combine the flexibility of FMS with the high volume output capabilities of DMS to create a more economically competitive manufacturing system. Moving on and looking more at the general implementation of RMS. So RMS implementation can take different forms. Some low-level examples would be just a single reconfigurable machine, or entire factories can be designed around the RMS philosophy. RMTs in particular, or reconfigurable machine tools, are a common example of RMS in action. These machine tools can change the orientation of, say, their spindles or value additive mechanisms to achieve different cutting setups or different production setups. Some of these machines even allow you to add extra spindles or specialized tools, easily interchanging all of these components on this machine depending on the manufacturing requirements at that specific time. Other more broad systems, more factory-based systems, can utilize traditional tools. Think a CNC machine into an assembly line with RMTs. Think of a production line where raw stock is fed into a CNC machine. That CNC machine can be bookended by two RMT modules, one that could, say, cut the stock to size, and another that could inspect the parts. All of these different units are completely independent from one another and can be reconfigured based on the needs of the factory at the time.
Just before we get into the specific case study that we want to cover with the presentation and the paper, we figured we could apply some of the knowledge that Toby just shared into other smaller case studies that detail the evolution of RMS in pharmaceuticals. So, starting with this earlier piece from about 15 years ago from MIT, they wanted to get the concept of RMS with medicine manufacturing. That's really their only goal. So, they figured the best way to do that was to create different lines of manufacturing systems specific to a specific drug. So, using this flow chart that we have here in the figure, we can say, there's drug A, B, C, and D. Each line is creating a specific drug, but let's say drug A and B have a very similar creation method or printing method for pills, but there's only one step that really differentiates the two. Instead of creating a completely new line just to create more of drug B while there's, a fluctuation in drug A, you could also just make everything modular so that one step could be taken out and one step can be, replaced. So the benefits of this is that it's obviously like RMS intends to be fast, directed towards a specific market, and very easy to switch out and change as, it comes with it being modular. The issue with this, especially in the early days of RMS in pharmaceuticals, is that because all of these modular systems are specialized, it's very difficult both to scale up and especially in the beginning, it's very difficult to fund because everything is so customized. When it comes to papers that would go on years later and specific case studies that would go on from like 10 years from the first paper we just showed you guys from MIT, this one was more personalized. So, similar to the first one where we had lines specialized on specific drugs, this specific case shows very vertical alignments with these modular systems. So, say Toby and I like need a personal set of drugs, obviously for medical reasons. I need a specific set of drug A, like four pills of drug A and 3 pills of drug B. And let's say we're setting up like a weekly basis of this, so it's 7 of that. Toby needs 3 of B and 4 of C. This system makes it so that each of our sets of pills for the week can be made in the same less than person sized manufacturing section of a facility. So they managed to make it much more efficient than the first study while also making it much more personalized. These custom sections can be, modularly taken out whenever they need to, depending on the not only the market value of each of these systems, but the personal need per patient per pharmacy. So, as you can imagine, scaling was still a very big issue, but they cut down on costs. And obviously, because it's more efficient, they cut down on time as well, which is pretty great. So, overall, when it comes to the evolution of RMS in pharmaceuticals in the early 2010s, they were just trying to put RMS into manufacturing medicine, which, resulted in case studies involving just lines of drugs being made, again, pharmaceutical drugs. And in 2020, they evolved that into making it more personalized because they realized that making a bunch of ibuprofen is useful for ibuprofen, but when it comes to more specific cases, you need more personalized lines of manufacturing. And nowadays, it's become very, very patient centered in that that's where the main market for pharmaceuticals are. So why not make it patient centered? And they're really just trying to hammer down precision and accuracy as much as they possibly can to not make any mistakes in these larger systems. That's the best way we can simplify without going into the specifics of the paper. But when it comes to things, trends going on in the future, we know when it comes to other manufacturing systems, AI is going to be put in there in one way or another. They generally know that AI is going to be involved. When it comes to the framework of these lines I was talking about earlier, they're going to be more generalized because they're getting a feel for how they're going to look in the future. So in good manufacturing practice facilities, they're going to look more of the same. And obviously, scalability has been an issue all around. So we also hope that scalability will be addressed in the years to come.
All right, so moving on to the methodology of our case study, which was a reusable smart factory designed for the pharmaceutical industry and drug packaging. The foundation of the system is a data-driven 3-layer architecture, as you can see here. So starting at the top, we have the perception layer. Its primary job is knowledge representation and generating production plans based on incoming data. It processes two main types of information: the real-time status data from the factory floor, like which machines are available, external demands, and new orders from the market. And this layer takes a customer request and figures out the best way to make it happen, creating a plan that gets passed down to the next layer, which is a deployment layer. This is kind of the middle manager layer. It takes the high-level plan from the perception layer and translates it into specific actionable instructions for the machinery. And it does this by scheduling corresponding machine function blocks, which are modular software components that control the hardware. And a key technology used in that is the IEC 61499 standard, which is for distributed control systems and allows for this kind of flexible scheduling. And we'll have more detail on that in a later slide. And lastly, we have the execution layer, which is the physical layer. It contains all the manufacturing hardware that performs the actual tasks. As you can see in the diagram, it includes everything from the robotic arms for drug grasping and the conveyors for medicine transport to the pill bottling stations and storage systems. This layer performs the work and sends information and status updates back to the perception layer, creating the closed loop system that can continuously adapt. Moving on to the ontology-based knowledge base. The knowledge base is what powers the perception layer. It's not just a simple database, but a system that's built on this ontology. And the foundation of that is the ontology. It's a formal way of representing knowledge, designing a set of components within a domain and the relationships between them. The pre-existing framework used in this case study is manufacturing semantics ontology, or MASON, and it provides a starting point with high-level classes like resources and operation, which were then adapted to specific needs of pharmaceutical production, such as defining the pharmaceutical machine or medicine production operation. And to build this knowledge base, two key technologies were used. One was the web ontology language, or OWL, and the second was the semantic web rule language, Swirl. OWL is the standard language used to formally write down the ontology. It defines the machines, the tools, and their properties. However, it does have its limits. So to represent more complex logic, like the specific operating rules for an arm or fault judgment conditions, Swirl is used. Swirl allows us to add a layer of if-then rules to the knowledge base, making it much more powerful and capable of complex reasoning. Speaking of reasoning, this leads us into our reasoning process. And once this knowledge base is built with OWL and Swirl, a reasoner is needed to think within that. So in this case study uses the GenaReasoner, which works like this. When a new production order comes in, the system queries the knowledge base to find the best way to fulfill it. The GenaReasoner analyzes the order requirements against the real-time status of all the factor resources, which are constantly updated in the ontology, instead of creating that closed-loop feedback. And it uses the Swirl rules to determine which machines are available and in what sequence they should operate. The final output of this process is a detailed plan that gets sent to the development layer, which is what enables the factory to be truly self-organizing and adaptive. Moving on to the IEC 61499 standard. This aids the development layer, and the core concept of this, it is the function block of that. The standard is an event-driven mode that is perfect for these distributed control systems. Think of it kind of like as a function block of software Legos. Each block is modular, reusable software component that encapsulates a specific control algorithm. These are very modular. They can be dynamically added, removed, or reconnected during an operation to create new logic on the fly. And this is what makes the system truly reconfigurable. And then to manage these function blocks, the system uses a two-phase deployment, which splits the deployment layer into two distinct parts: a design phase and an implementation phase. The design phase is the upper, more abstract phase. It acts as the high-level conductor. It receives the production plan from the perception layer and schedules the corresponding function blocks into the correct sequence. This phase is device independent. It's focused on the logical flow of operations, not the specific hardware. And in the system, a central server is used to host that design phase. Secondly, the implementation phase, on the other hand, is deployed directly on the runtime environment of each machine. For example, a Raspberry Pi that's connected to a robotic arm in the process. This phase kind of acts as a low-level foreman on the factory floor. It receives the management commands from the design phase and triggers the specific function blockchains that are directly responsible for controlling the PLCs, the motors, and the sensors of that machine. The two-phase approach separates the high-level flexible planning from low-level device-specific execution, giving them both great agility and robust control over the whole process here.
Okay, so our next section will be an analysis of the advantages and challenges of the proposed reconfigurable drug packing system, categorized by the three main layers of the system. The physical system, found in the execution layer, the ontology-based knowledge base, found in the perception layer, and the distribution controlling and flexible functionality reconfiguration system, found in the deployment layer. First, we'll discuss the various aspects of the execution layer. The physical system has a modular design, which is highly compatible for easy scaling. There is clear division between the pill packing agents and the delivery agents. The embedded Raspberry Pis make each agent operate semi-independently, which enables local decision-making, reduces central processing load, and increases system responsiveness to self-reconfigure in real time and for different types of pill packing processes at the scale used in this study. Raspberry Pis also provide support for edge computing, which allows for lower latency and resilience against network failures, since the local devices can still operate independently, and risk of bottlenecking is mitigated since the system isn't controlled by one central controller. Using Raspberry Pis controlled PLCs ensures reliable real-time control over the physical system components of the system, such as motors, sensors, and cylinders. The integration of RFID tags and readers allow for dynamic routing and traceability in order to reduce errors and improve the efficiency of the process. While there are many benefits to this setup, there are some potential issues present as well. Raspberry Pis themselves are cost-effective but may not be industrial grade, so depending on tax complexity and processing power, the real-time performance may be limited, especially under high loads or with many agents, which brings the issue of scalability to the forefront. This system is also highly dependent on the accuracy of the RFID readers, so misreads, interference, or tag failures can cause processing or routing errors. Continuing on to the ontology-based knowledge base, let's explore its implementation in the system. One of its greatest strengths in its function as a common semantic layer. Ensuring the alignment of semantics in data format, protocols, and error handling across boundaries is essential at layer interfaces. Using the architecture of Mason, OWL, and Swirl, heterogeneous data is homogenized under a unified framework. This allows the system to reason about relationships, constraints, functions, and implicit knowledge. It also helps generate production plans or adjustments based on changes in the machines themselves, demand, or issues. The ontology enforces expert domain knowledge to guide decisions, avoid invalid configurations, and ensure compliance with industry guidelines. There are, however, some downsides to the use of this knowledge base. Ontology reasoning is computationally heavy, and as such can bottleneck as the number of rules, relationships, and entities grow, even with the current multi-controller structure and as the domain evolves. Missed relationships or misinterpretations or constraints can lead the system to generate invalid or suboptimal plans. So the quality of the outcomes is heavily dependent on the ontology's dependability. There is a challenge in the data quality and bridging the gap between the semantic ontology and the real-time data gathered by machines and sensors, which may create noise, be delayed, or come inconsistently. The use of this ontology presents a challenge in using the special ontologies and semantic technologies. It may be hard to find workers already familiar with the specific tooling, troubleshooting, and technology, or workers will need to be trained. Using this knowledge base also relates heavily to the scale of the production system. So overhead cost of the complex ontology-based system may outweigh the benefits in simple factories. Moving on to the final section, let's consider the use of the IEC 61499 standard for distribution controlling and flexible functionality reconfiguration. IEC 61499 is designed for modular, event-driven function blocks in distribution. This makes it highly compatible with reconfigurable systems with logic control, allowing for flexibility and adaptability to changing demands or failures. Using a recognized standard gives the advantage of interoperability with other systems or future extensions. However, it is not widely adopted in industry compared to IEC 61131, which is used for PLC programming with a cycle-based execution model. So finding compatible industry tools, engineer support, and device compatibility may be an issue. This also means that the PLCs used in the system need to be specifically compatible with IEC 61499, or custom adapters or APIs need to be used to bridge the logic types in integration. IEC 61499 itself can require more memory, CPU, and timing than the Raspberry Pi can provide, which may cause issues in real-time response and introduce the risk of overload or crash under the high task complexity. Dynamic reconfiguration is also highly complex, and there is a risk of state synchronization issues, timing issues, or instability if the reconfiguration isn't properly handled because logic changes during runtime. This can cause partial failures or inconsistent control commands that could affect pill packing or transport. Then, if there's no rollback or a new block fails, the system may not revert correctly, which will create cascading failures. We'll continue finally to our conclusion. The modular structure is conceptually attractive as it creates a separation of responsibilities, which helps easier maintenance, expansion, or replacement of each layer independently, and creates clarity in the flow of materials and data through the system. The closed-loop feedback structure supports responsiveness for adaptations or reconfigurations in real time via data from the execution layer back up to the perception layer. The synergy of this system is its greatest strength, allowing for dynamic responses, expert knowledge, and flexibility as demands change. When thinking about future expansions and implementation of the system at a larger scale, there are some concerns seen, particularly when it comes to data and command flow. At current capacity of the industry, one of the biggest issues tends to be latency and communication overhead. In this system, there is potential for delays or data bottlenecks as data flows through each layer. Arranging for the seamless data flow between layers poses a challenge in itself, particularly with bottlenecking concerns in the perception layer. Fallback or failover strategies are not really discussed for the system and should be considered in industry applications before implementation to ensure the system is reliable and robust against failures. These drawbacks are less likely to create problems at the current scale and state of the system, but can be more apparent at a larger scale. There is also the point of cost and deployment time when scaling to a more robust infrastructure and more tooling. These factors can make practical deployment a challenge. Overall, the system in theory is highly flexible and aligns strongly with the cyber-physical system ideals. As long as technologies are also upgraded as the system expands, this system can be compatible for growth, adjustment, and improvement with the Industry 4.0 principles in mind. That brings us to the end of our presentation. Thank you for your time and attention, and have a good day.